Okay guys, so we are back again. We're just looking at the last question for A and for B on this paper. I've done a question from number 1 to number 3, so now I just a continuation. So we're saying for 4A, they are saying find the general solution of the partial differential equation using the separation of variables method. So this is the PDE that we have. It's just 8 marks. We're going to find the general solution obviously, and then this is a continuation for 4B, which state that continue the above problem, discuss all the 3 possible solutions for the PDE given that these are the condition. So let's start with A, just find the general solution for this PDE. So how do you go about this one? It's the same approach that I did with the wave equation video. It's in the, you just go and look at the wave equation video. It's the same thing, just that this time around with respect to Z, but it's just the same thing actually. If you look at that video, you'll basically know what we're about to do right now. So so let's solve this one. So we are doing 4A. So pretty much it's the same thing. Let me just make sure that I have everything here. So we are looking at 4A. So we are given dou Z, dou x squared minus dou squared Z, dou y squared is equals to 0, right? We want to find the general solution for this one. So how do you go about this one? So again here we need to assume a trial solution. Which is Z xy is equals to x y, right? Which we can just write it as in this form as x y. So this is our general solution, our trial solution, sorry. So now we need to use this simplified version of our trial solution to find the second derivative of Z with respect to x and with respect to y, and then you're going to substitute there. And so let's do it. So for this one, if we're differentiating, so we are going to differentiate this with respect to x. So this is going to be x prime y, right? And then if we find the second derivative with respect to x, is going to be double prime y, right? So again, with respect to differentiate Z with respect to y, it's going to be x y double y prime, and then the second derivative with respect to y is going to be x y double prime. So now we can just take this and substitute it in our main equation that we're given. So we are going to have x double prime y minus x y double prime is equals to 0. So you can just take one term to the other side. We are going to have this is equals to x y double prime. So from here, what do you do then? You just collect like terms. So x variables on one side, y variables on one side, keep the derivative of the highest order as the numerator. So you're going to have double prime over x is equals to y double prime over y. So from here, then what do? You're going to equate this equation to mu, where mu is a constant. You need to write this. When mu, we're defining mu is a constant. Why is it a constant? Since mu is independent, this is independent of x and y. It's independent of x and y. That's why it's a constant. So I can split this equation into 2, whereby I have x double prime x is equals to mu, and I have y double prime y is equals to mu. So I can rewrite these equations as minus x is equals to 0, and also this s minus mu y is equals to 0. So from this point, we're just going to apply for both of these equations to the second order. PDE, second order PDE. So you have second order PDE. So you're just going to find the auxiliary equation for both. So you use the D operator again. I won't go through that since I did it in the first video. So this is just going to be m squared minus mu is equals to 0. And here you are going to have n squared minus mu is equals to 0. So here m is equals to plus or minus root mu, and here n is equals to plus or minus root mu. So these are the two distinct values of m and n. So obviously, if you have two distinct values, your solution for this one, it's going to be x is equals to a e to the power root mu, right? X plus b e to the power minus root mu x, right? And then for this one, for y, we are going to have, since there are two distinct values, we are going to have c e root mu plus d e minus root mu. It's the same as the approach that I took with the wave equation. So from here, we know that a, b, c, d, these are constants. So in order for us, we have x, y, right? We said z is equals to x, y. That was the trial solution that we assumed earlier. So now we can write z as x is what? It's a e x plus b e minus mu x. Y is c e root. This is y. By the way, this is y. Root y plus d e minus mu y. So this is our general solution. That's a. So that's how you get your general solution. That was a. So now we are looking at b. So we are using this general solution. We need to discuss three possible solutions for the PDE because we have values of. Because we are looking at the values of mu. Our possible solutions are based on the values of mu that we assumed or that we introduced while we're formulating the general solution. So one thing here, we are going to have three cases, right? So the first case we are going to assume, that mu is greater than 0. That's the first case. So if you're assuming that mu is greater than 0, obviously it's positive. It's a positive integer. It's a positive real constant. So you're going to say let mu be a positive constant, which is represented by p squared, where p is a real constant, isn't it? Where p is a real constant. So if mu is equals to p squared, you're going to come back to these two equations. Where there's mu, we substitute p squared. So we are going to have x double prime minus p squared x is equals to 0. Y double prime minus p squared y is supposed to be capitalized. Y is equals to 0. So from here we do the same thing again. You find our auxiliary equation, n squared minus p squared is equals to 0, and n squared minus p squared is equals to 0. And then from here we can see that these are the auxiliary equations, auxiliary equations, and from here we can see that m is equals to plus or minus p, and n is equals to plus or minus p, and then again we write so again from here we can see we can rewrite z as xy, but now in terms of p. So we are going to have z is equals to a e, instead of roots new, we are going to have now px plus b e minus px, right? And then c e py plus d e minus py. So basically it's the same thing here. Instead of this we have p, because we represented mu as p, right? So this is, we are doing the first case. So now we need to apply the boundary condition. So these are the boundary conditions that we're given. So these boundary conditions are basically saying here, so for this one can be split into three. They're saying z y is equals to 0, z l y is equals to 0, and z x 0 is equals to 0. That's what I'm saying. So these are the 1, 2, 3, they're all equals to 0. So they just include it in one long equation. So basically that's it. So we're going to evaluate the first one, this one. We're going to evaluate this one. So let's evaluate the first one. So we're evaluating z when x is 0, y we are saying z is going to be 0. So which means z is going to be 0 when x is 0. So when there's wherever there's x we have 0. So e to the power 0 plus p e to the power 0. Then we have c e py plus d e minus py, right? So this is 0 for a plus p, and c e py plus d e minus py, right? So from here, and then this is very important. So we are saying this side is equal to this side, which means this side is 0. So what can make this side 0? That's very important. So you need to write here, since we have exponential equations, exponential terms here, so you need to state that e py plus d e minus py cannot be 0 for all values of y, which means therefore a plus b, this term, that means a plus b, that term is the one that is equals to 0, which gives us a new equation, a is equals to minus b. So we come back here. So now from this one, where there is a, we substitute with where there is so from this one, where there is a, we substitute, where there is b, sorry, where there is b here, we're just going to substitute with minus a based on this equation. So we can rewrite that one as z is equals to a e px minus e minus p x c e py plus d e minus py. So what did I do here? Here this was a, this was minus a, because I substituted here. Where there was b here, I substituted with minus a using this equation. So from this point, what do? You evaluate the second. You evaluate the second boundary condition, whereby we are saying when z is L, when x is L, sorry, z is 0. For the graph, there is a graph for this that you can actually see. You can represent this graphically. Just go and look at the video for wave equation. I did the graphs so that you can see what I'm talking about, so that you can also understand the binary, the boundary conditions. So let's evaluate this one. So 0. So that means wherever there is x, we have what? We have L. So A EPL minus EPL CEPY plus D E minus PY. So from here, obviously, this is an exponential, so they cannot be zeros. In order for the entire thing to be 0, that means A has to be equals to 0, right? For the first condition, we stated that this cannot be 0, obvious, and again here this cannot be 0 because these exponential terms. So that means here A is what? A is 0. So since A is 0, that means since A is equals to minus B and A is 0, that means B is also 0. So A and B are zeros. So what does this mean? This means this solution is disregarded, or is not feasible. This is disregarded. This solution is disregarded. So it cannot, mu cannot be greater than 0. That's what that means. Mu cannot be greater than 0 for this general solution. So let's look at another case. Okay, if mu is not positive integers, then let's assume that mu is equal to 0. Then case 2, we are going to assume that mu is equal to 0. So if mu is equal to 0, we are just going to remember we had our second order differential equations. Right? So now mu is equal to 0. That means x double prime is equal to 0, y double prime is equal to 0. So from here, we want to find the general solution for x and y. So what do you do? If the second derivative is 0, the first derivative is what? It's a constant, right? And then the variable is going to be a linear. What am I talking about? If you have y is equals to 2x plus 3, so y prime is going to be what? 2, y double prime is going to be 0. So this and this, we are at this state now. So if we integrate this twice, we are going to get a linear expression, right? So that's the kind of intuitive thought that we're going to use here. So we are going to find the value of x and y in our case. So here so now we can say x here is equals to ax plus b, because we can, if we differentiate this twice, we are going to get this, right? So, and here the same thing, y can be equals to py plus q. So again, you need to define every new term that you a, b, p, and q are constants, right? These are constants. So now this is what we have. So what's the first thing that we do here? So we write z is equals to x. Our x is ax plus b, py plus q, right? So from here again, we apply your boundary condition. We apply the first one where x is 0, z is 0, right? So z is 0, where x is 0, so ax is 0, so we're going to have b here, by plus q, isn't it? So from here, again, since py plus q cannot, this one cannot be 0, right, for all values of y. You can basically say whatever value you put here for y, it cannot give you this as 0. Even if you say y is equals to 0, you are still going to get q, right, as a constant. So this cannot be 0 for all values of y. That means therefore b is equals to 0 here. in order for this equation to be satisfied. Okay, so if b is equals to 0, then now you can rewrite z as ax, since here b is 0, so we are left with ax py plus q, right? So we apply this, from here we apply the second boundary condition, where now x is L, 0 is z is 0, so this is going to be AL py plus q. So again, py plus q cannot be 0, so that means what? That means a is equals to 0, right? Therefore, since a is equals to 0 and b is equals to 0, therefore this solution is disregarded. This solution is disregarded. That means mu cannot be equals to 0. So now we need to move to the third case, where now we are looking at mu might be less than 0, where case 3 we are saying, what if now mu is less than 0? So if mu is less than 0, we're just going to say let, which means it's a negative integers. It's just a bunch of negative integers. So mu is equals to minus p squared. Again, where p is a real constant. P is a real constant. So we have minus is equals to 0, y minus mu, y is equals to 0. So now we are saying mu is less than, so where there's mu, we substitute minus p squared. So we're going to have x double prime plus p squared is equals to 0, y plus p squared, y is equals to 0, right? And then again, we need to find our auxiliary equation. Auxiliary equation, p squared is equals to 0, using n squared plus p squared is equals to 0. This is our auxiliary equations. So from here, we have auxiliary equation. So our value of m, this is going to be plus or minus ip, since it's square root of a negative constant, it's I. So again here, m is equals to plus or minus ip, right? So now we have complex numbers. So remember, if you're evaluating a second order derivative differential equation with a complex number, we are going to have x here is going to be evaluated. Remember, if you have m is equals to alpha plus or minus I beta, we are going to have your y is equals to, it's going to be equals to e to the power alpha x. Then you're going to have a cos beta x plus b sine beta x, right? So if you have a complex number, this is your general solution. But as you can see, alpha here is 0, right? So this is 0 for us, so which means this term is 0. So we're just going to only evaluate this part. So now here we're just going to get x for this one to be a cos, our alpha is p here, so px plus b sine px, and then y is going to be the same, d cos py plus c sine py. Okay, so now we can write z as a cos px plus b sine px, right? And d cos py plus c sine py. So now we have this. Again, we substitute, we write, we evaluate the boundary conditions when now x is 0 and z is equals to 0. So 0 is equals to a cos 0 plus b sine 0 d cos py plus c sine py. Obviously a, b, c, d are constants. So if you evaluate this, you're just going to be left with 0 is equals to cos 0 is 1, sine 0 is 0. So we are going to be left with a d cos py plus c sine py, right? So from here, obviously these these trigonometric functions, which means they alternate. So you can just state again that d cos py plus c sine py cannot be 0. That means a is equals to 0. So if a is equals to 0, we can rewrite this general solution where now a is 0. So we are going to have this part. So we are going to have z is equals to b sine p x d cos py plus c sine py. So again, we evaluate the second boundary condition, which is equals to 0. So when x is L, z is 0. So 0 is equals to b sine p. When x is L, we have d cos py plus c sine py, right? But then now we should be careful. Then which one is 0? Obviously, we said this cannot be 0, right? And in this case, b also cannot be 0, because later on b is going to be actually our solution. When we are evaluating the Fourier series, b is going to be our solution. So at this point, we are going to say b is not equals to 0. Therefore, and also this is not equals to 0, but I stated it earlier. So b is not equals to 0, which means sine pl should be 0 for this equation to be satisfied. This is supposed to be 0. So now, so this is where everything changes, where we are saying sine pl is equals to 0. So that means pl is equals to sine inverse of 0. So sine inverse of 0. So if you draw, so this is going to be pl is equals to n pi. So this is going to give you n pi. How does it give you n pi? So if you draw your sine graph, that is oscillating. So whenever, where sine is 0 here, this is y is equals to sine theta. So sine is 0 here, sine is 0. So the solutions where sine is 0 is what? Is 0, pi, 2 pi, 3 pi, continues 4 pi. If it continue to be 4 pi, 5 pi, 6 pi, 7 pi. So where the graph intersects x-axis, we have a solution, right? So now our solutions are what? 1 pi, 2 pi, 3 pi, 4 pi, continues, right? So 1, 2, 3, 4 is the n here. So you can say that where n is just positive integers, where n is a member of positive integers. n is a member of positive integers. So now from here we can make p the substitute of the formula, which is n pi over l, and then we come and substitute here where there's p, where there's p, where there's p, we substitute n pi l. So z is equals to b sine n pi over l x d sine n pi over ly plus c sine n pi over ly. So this is what we have. So now from here I'm just going to multiply the coefficients, whereby I'm going to say, since I'm going to, when you open the brackets, multiply with the coefficients BD, I'm going to say it's AN, and BC is going to be BN. So now from here, no, this is BC, sorry, this is BC because I'm distributing B inside. I can rewrite this as sine n x is an sine n y plus bn. Oh, this is supposed to be cos. Sorry, this is supposed to be cos. Yes, I made a mistake. It's supposed to be cos even here. This is cos, and then bn sine n pi over n y, right? So then from here, so if we substitute the value of n, if we substitute n is equals to 1, we get a solution. N is equals to 2, we get a solution. N is equals to 3, 4, 5, 6, 7, 8. So we are getting solutions for as long as n is a positive integer, which means we can sum all of those solutions. So we can represent this as the summation when n is equals to 0 to infinity of sine n pi over l x an cos n pi over ly plus bn sine n pi over ly. Then this is, so we can represent this as a series, and then now we apply the third boundary condition, whereby we have z x where z x and y0 have 0 here. So I'm applying the third boundary condition, which is this one. I'm applying this one, I'm applying this one, right? The third one, this one. I've been applying these two, but now I'm starting to apply this one. I'm also going to apply this one. So I'm applying the third one here to evaluate this. So this is it. So now we are going to have 0, z0 when y is 0. So we're going to have, this is the equals to the summation of n is equals to 0 of sine n pi over lx. So when y is 0, which means this is going to be 1, this is going to be 0, right? When y is 0. So here we're just going to have basically an, because all of this will be 0. So we're going to have an, since this is 1. So we're going to have an like this. So we can rewrite our z as the summation, and n is equals to 0 to infinity of sine n pi over lx. So we have an, so here we have b. So okay, sorry, in order for this to be 0, that means an here is equals to 0, right? Because this cannot be, sine n pi over l cannot be 0 for all values of n, right? So an is 0. So if an is 0 here, which means if we substitute it here, this is going to be 0, right? So now we are going to have our new one is going to be bn sine n pi over l, sine n pi over l y. So this is what we have. And then now from here, what we basically do, we apply the last boundary condition, the fourth one, which stated that dz dy of when x and when y is 0, this is said it is equals to, this is equals to f of x. So we need to differentiate this with respect to y. So, and then where there is y, we substitute 0. That's all. So del z del y, this is going to be, they are telling us that it's going to be f of x, right? Which is going to be, when you're differentiating this with respect to y, you're going to get, so which means sine n pi over lx is a constant. This is just going to be a constant because we're differentiating with respect to y. Let me use the curly bracket here. So now inside you're going to have, differentiate this with respect to y. We are going to have minus bn, right, cos, differentiating, differentiating, it's not minus, it's just going to be cos n pi over l y times the derivative of what is inside, which is n pi over l, right? So from here, so we have, and again we are told that y is equals to 0, right? Which means here y is equals to 0. If y is equals to 0, this is going to be 1, right? All of this is going to be 1. So del z, or let me just write f of x, because this is f of x is equals to infinity of sine n pi over lx. This is going to be n pi over l bn. So from here, this is, if you look closely, this is a Fourier. This is a Fourier series. This is a Fourier series, and remember, for a Fourier series, we evaluated b. We evaluated bn as what? We evaluated bn as 2 over l. You need to remember this, from 0 to l of f of x, the function itself, sine n pi over l we did. So if you don't have any prior information about Fourier series, you just need to go and look at this. So we said this is the general formula for bn. Since bn, when you're looking at Fourier series, we are saying this is one of Euler's, this is Euler's constants, right? So but then our bn here is, it comes with n pi over l, which means we have n pi over l. bn is equals to 2 over l integral from 0 to l f of x sine n pi over l x dx. Therefore, which means Bn is equals to what? If you take this side, we are going to have 2 over n pi, because this and this will divide. 2 over n pi 0 to L f of x sine n pi over L x dx. So that's the end of this problem. So which means since we are getting the value of Bn here, we are getting the value of Bn, that means the third case is satisfied, which means mu can be less than 0. So that's basically it. We just discussed the 3 solutions, and we've got that the third solution, after further evaluation using the Fourier series, we got the value of Bn, one of the constants, and that tells us that it cannot be disregarded, and it is mu less than 0 is defined. So now this is basically it. So just go and watch also the wave equation. I did the same thing. I was even more detailed there in terms of the graphs and how to evaluate the boundary conditions, how you can represent them graphically. So yeah, this is it. Thank you.